Okay, so we're doing triple integrals. This is basically summing a function through a solid. A function evaluated at points times differential volume through a solid. Let's say all points in a solid. Okay. All right, so the differential volume is going to be sort of a prism, but it doesn't have to be a prism. Sometimes it'll be a wedge shape. Having trouble, sorry. Okay, so here's my differential volume, dV, which is going to be dz, dy, dx in any order. Okay, and basically we evaluate, and let me just do something real quick here. So somewhere in the middle of this, I wanted to put a point x, y, z. Okay, so basically what we would do is define a triple integral over a solid. And I guess I go ahead and draw the solid. So give me a sec here while I do a picture of a solid. I think it looks like maybe, I don't know what that looks like. Okay, so this solid is called Q. And I can take my little differential prism here and maybe put a copy of it inside. Okay, so basically we need to sum over all points in Q. Okay, and so I think we can just do triple integral now. Over the solid Q. And we'll have the function be f of xyz dv. And this is going to be defined as a limit of course. And I'm going to have three, it's going to be a triple sum. So I'm going to have an m going to infinity, an n going to infinity, and a p going to infinity with a triple sum. Okay. Where I'm evaluating f of, it'll be f of xyz at some random point. And it'll be dv, or delta v, I guess I should say. Okay, and then there's going to be subscripts, of course, on all of this. A huge mess of subscripts. So you can have, I don't know, 3 subscripts for 3 indices, or 3 sums. So there's going to be like an an xijk star, like that. Same thing with y and z. Oops. Like that. Like that. So I will go from 1 to m, j from 1 to n, and k from 1 to p. Like that. So that's, and without going into too much detail, that's sort of the idea of how these are defined. And I don't think you'll get any theory on these. But after we had defined this sum for a double integral, we went straight into a theorem that told us that we could do iterated integrals. So I'll remind you of that. So here's 15.1. We had this rule of iterated integrals, where you just do an integral and an integral. So I want to do the same thing with a triple integral. And so the theorem just says as follows, that the triple integral, and I have to do one more thing before I go there. So hang on a second, I need to project this region here down into the XY plane. So I'm about to grab my two-dimensional part of this graph and just sort of project it downward. And I'm going to try and line that up nicely. Hang on a sec. This is the shadow, or otherwise known as the projection. So we'll call this R down here and put some coordinates in now. Okay, so R is the projection of the solid into a coordinate plane. It doesn't have to be into the XY plane. Okay, so this theorem is kind of what you'd expect for iterated integrals. So the triple integral over Q of f of x, y, z dv. Okay, so this is actually just a double integral over this region R of a single integral of our function f of x, y, z. And then we'll integrate dz here. And where the limits on z go from a lower surface to an upper surface. So whatever the lower surface is, if z is a function of x and y, then the lower limit will be that lower surface. And of course the upper limit on z will be the upper surface. Okay, and then so you just evaluate that integral, and in the end, once that's done, this just becomes a double integral on the inside, and you'll do that dA. Okay, and again, now you're integrating over R, which in this, the way I've drawn this is just a region in the xy plane. Okay, so that's how you evaluate double integrals, but they don't have to be from lower surfaces to upper surfaces. They could go from left to right surfaces, or front, or I should say back to front surfaces. So there's lots of ways that this can play out. They just wanted to take a real quick second to talk about the different applications that we'll discuss about triple integrals. And it shouldn't be a big surprise to note that our primary applications will be related to mass, centers of mass, moments, and moments of inertia. And then there are analogies to all of those in probability and statistics, where in physics, the f of x, y, z can be a mass density function. And you can, when you integrate that and versions of that function, you can get all the moments and the mass. But if f of x, y, z is a probability density function, then all the moments are used to compute the means for each variable. Center of mass will be an x bar, y bar, z bar in physics, but that'll be thought of as the average, but that's sort of a vector now in statistics. And as we've said before, the moments of inertia become variance in statistics. To the next page. I want to do just evaluating an integral. So here, evaluate a triple integral over a solid Q of x minus y dv, where Q is bounded by the parabolic cylinders z equals x squared minus 1 and z equals 1 minus x squared. And where y goes from 0 to 2. Okay, so that's the problem. And so we have to learn how to make sense of this. Obviously, you're integrating from surface to surface. Right now, I've given you two surfaces in Z. Let's go ahead and see if we can pull this off. So I'm sort of drawing a parabola, which is going down and sort of touching the x-axis like that. And obviously this is a y-axis coming down this way. Okay, this is x here. And then you need several copies of this parabola. I'm going to try and just flip it. I might try and do a better job drawing it too. Let's see if I can do a better job. I don't think so. So sad. Let's see. Which one's better? It doesn't matter. Okay, so I'm going to rotate that and try and get a copy of it that represents the cylinder on the bottom. Ooh, did not mean to do that. It's pretty good. Okay. I'm going to rotate this whole thing a bit. Okay, so the top one is z equals 1 minus x squared. And of course, the bottom is z equals x squared minus 1. So I've drawn those as curves, but they're cylinders, which means they are unconstrained in one variable. So I think what I would do is maybe make a copy of the y-axis. So another line parallel to the y-axis and maybe put it right there. Not going to be permanent. And another one down below. These are just guidelines for me right now. Okay. And yeah, I need to copy those two parabola is further down, so I'm going to make a copy of those two guys if I can figure out how to grab them. Put them down here, like that. Okay, and now I'll probably get a little more serious with some of my lines. Or just more guideline. I need a z-axis, I guess. So I'm going to pop a z-axis up here. And I'm about to do some guidelines, as I said, so I'll be erasing some of this. Like something in me wants to put a guideline right on the top of this thing like that. But that's not going to be a line of sight. See, what you need here is something that is like a vanishing, a point where things vanish. So I'm trying to put that in, but it's not going very well. It's giving me trouble. All right, that's better. Okay. Need some of those down below too. So I'm going to put a vanishing line down below, sort of like that. That looks pretty good. So I think I'm going to cut off some of that and hide it. So, oh, I didn't need that. Let's see what I got here. Okay, so you got the top surface, you got the bottom surface. I've got y going from 0 to 2, I guess. So I'll put an identifier here where y is 2. You know, and I don't know if shading is optional. And at this point, I don't know how much more time I want to spend. I don't want to spend that much more time on this. So I'm starting to feel like I don't want to. Okay, so I think I'm going to leave it at that. Maybe just do a little bit lighter color in here and we'll call it quits. Okay. Now, so you have a top surface and a bottom surface. You kind of need to know what these lines are down here, these intersections. So right there, I need to know that value. What is the value of x? And probably in the back as well. Anybody want to take a stab at those? So I've drawn 2 arrows to some x coordinates. I need those. -1 and 1, good. So x is 1 in the front, x is -1 in the back. And you know, forgive me, but I'm going to go ahead and just very faintly do a little gray region in the plane. Because that's, we're going to have to integrate over that in the xy plane. So just real faintly, I'm going to color that in. I don't know if that's going to be visible or not. Let's see how it comes out. So in gray, I'm adding a little bit down here. So the solid is Q, but down in the XY plane, I have a little thing that I'm calling R. Okay, but the solid is Q. Okay, so here we go. Triple integral of x minus y dv over q. Okay, and as we say, this can just be thought of as a double integral over the region R down there in the xy plane with an integral inside of it of our function x minus y. This would be dz, okay, and then once that's done, you'll just be doing a double integral, so that'll be over an area differential, okay. But the limits on z will be bottom surface to top surface. So on the bottom, z is x squared minus 1. And on the top, z is 1 minus x squared. So integral, integral, integral. This is the iterated part. X minus y, yep, still dz. And then you have 2 orders. You can do dy dx or dx dy, like that. Okay. Limits on z don't change. They are 1 minus x squared to x squared minus 1. And then if you were to graph this thing in the xy plane, then of course, as was pointed out, x goes from -1 to 1. And y goes 0 to 2. So it's a rectangle, and rectangles are super easy, right? Y equals 2, y equals 0, x equals -1, x equals +1. So those are your limits on x and y. And the region is R. Okay, and you evaluate this just like a double integral. Okay.
Quick question, Professor. For the z upper limit and the lower limit, did you reverse it?
Yeah, x squared minus 1 is our lower limit. Thank you. Thank you so much. Try and get it straight. All right, let's evaluate this thing. Now again, initially you're integrating in z. So you treat x and y as constants. So -1 to 1, then 0 to 2, and then we're just going to keep the x minus y, but then put a z outside. And just so there's no confusion, I'll say z equals x squared minus 1 to 1 minus x squared. And then it'll be, once that's done, then it'll just be dy dx a normal double integral. Okay, and then I'll come over here. Times z, so for z you're going to do 1 minus x squared minus x squared minus 1, like that. And then maybe we could just squeeze this in and say -1 to 1, 0 to 2, and it's x minus y still, but then that part is going to be, is it 2 minus 2x squared? Maybe we just write it as a 2 times 1 minus x squared. And then dy dx, I believe. Okay, any questions? All right. The 1 minus x squared is actually a constant, so you could actually pull this out. So because we're doing y right now, dy. So I almost want to put the 2 all the way out front, the integral from -1 to 1, and then have the 1 minus x squared be here. You can't bring out x minus y, so let's do the integral 0 to 2, and then just have the x minus y here, and that'll be dy, and then dx when we're done. Okay. So this looks easy. So 2 integral -1 to 1. You can't do the outer integral till the inner is done. Okay, so here we go. We're doing the antiderivative now. So of x minus y, this is dy. So you're going to have an xy, where y goes from 0 to 2. Okay. And then minus 1/2 y squared, where again y goes 0 to 2. And then when it's all done, it'll be dx. Okay, any questions? Okay, and so here we go. 2 integral -1 to 1. We've got the 1 minus x squared. And then inside here, it looks like just a 2y. Because the 0 part is going to vanish. So when y is 2, is that 2x? My apologies. When y is 2, it's 2x. When y is 0, it vanishes. And on the next one, when y is 2, you get 1/2 times 4, so that's just -2. Okay. And then a dx. Probably take out another 2. I can call it 4, integral from -1 to 1. Now here, looks to me, you're gonna, so it's x minus 1, so 1 minus x squared times x minus 1. So you're going to have an x minus x to the third, and then minus, let's say, plus x squared, and minus 1. This part is the odd part, so the odd part goes to 0. Okay, so you can just do the even part. So you're going to have a 4, and then you have the integral from -1 to 1 of just x squared minus 1 dx. So then this is easy. So we'll go for third. Well, let's just put it inside here. So you're going to have a 1/3 x to the third from -1 to 1, and then minus x from -1 to 1, like that. And so that's going to be a 2 in each case. So this is just going to be 4 times 2/3 minus 2, I think. Now, I'm not sure, but I think, let me think now. Let's see, 2/3 minus 6/3 is -4/3. Is that -16/3? Okay, and again, there's no application. It's just a problem. Okay, this couldn't be a volume because it's negative. You're just evaluating a function that is predominantly negative over this region, and that's why the integral came out negative. Okay, if it was predominantly positive, meaning it comes out positive, then the integral would come out positive. Okay. Any questions about that one? We gotta do more, so let's keep going. Here's a fact that I'm not going to do an example of. Fact, recall that if you do a double integral over a region R of like just 1 dA, this comes out to be the area of R. Okay, so also, oops, triple integral over Q of 1 dV is the volume of Q. So a lot of times, if Q is a region if it's a solid that you recognize, like a sphere or a cylinder, a circular cylinder, I mean, you might know the volume of that, in which case nobody asks you to evaluate triple integrals to find volumes if you already know the volume. Okay, so keep an eye open for problems like that. I love those on exams, just to hopefully save you some trouble on a problem, but I'm not going to do an example of that right now. You'll see it as we go. Okay, so here, the instructions are to draw the solid, of integration, then change the order of integration, to dy dx dz. Okay, so here comes. There's no function to integrate. You're not being asked to integrate this. This is an application of doing nothing more than just sort of analyzing the region. And this is all about setting up integrals, which is half the battle. Okay. So it's dz dx dy, and we're changing it to dy dx dz, which is not simple. So first thing, the lower limit on z is 0. The upper limit on z is 1 minus x squared. Okay, and we've already looked at that one. Next one, for x, the lower limit is 0. The upper limit is 1 minus y. Okay, and then the limits on y are just 0 to 1. Okay, and I think I'm going to bring this down and make some space that I can write. Okay, so you have to remember that the inner limits are a curve. So down below is the surface, sorry, The innermost limits are surfaces. So down below, that's a surface, z equals 0, which is the xy plane. Okay. The upper limit on z is also a surface. It's the parabolic cylinder. So it's z equals 1 minus x squared, and in parentheses, parabolic cylinder. Okay. Now, surfaces innermost, curves outermost. So these two limits will be curves. This is curve, that's a limit on x. So it's x equals 0 in the xy plane. Okay, and above a curve, because these are limits for x, the curve is 1 minus y, x equals 1 minus y. And again, it's in the xy plane because those are the variables of integration right now. I think I'm frozen. Oh, here it comes. There we go. Okay, and then surface to surface, curve to curve, point to point. So this is a point, y equals 0 on the y-axis. And then, of course, the point, y equals 1. Again, on the y-axis. So we start in 3 dimensions, then we go down to 2, then we go down to 1. Okay, looking for questions up here. I don't see anything. Okay, probably need to sketch it, unfortunately. So I'm going to start with the cylinder. You might notice that the lower limit on x is 0, so we don't have to do negative values of x. So I'm going to start just by, let's see if we can draw this thing here. Okay, so start just by trying to draw this parabolic thing that comes down like this. It's not circular, remember, it's parabolic. So it comes down, I can't do it. Okay, third try. Okay, that's pretty good. Okay, now some of the things I'm about to draw, I'll be erasing. Okay, first of all, a guideline up on top here. Oops. Okay, so this is just a guideline that I'm going to put right there. And then another copy of that parabolic thing. Over here somewhere. Okay. And then I'll connect those. Then again, a lot of this gets erased in the end. Just got to remember this whole thing gets sliced by y equals 1 minus x. So I got to figure out where that is. In the xy plane, y equals 1 minus x. And let me see if I can do this. I'm going to need another guideline, so real quickly, give me a sec. Okay. Again, this is just temporary. Okay, y equals 1 minus x is going to go out. Oh, I did not mean to do that. It's going to go across diagonally. Oops, darn it. I get it. Okay, so y equals 1 minus x is going to go like this. So right here, y is 1. Over here, x is 1. Okay, now that plane is vertical. Z is not mentioned, so Z is unconstrained there. So I'm going to draw a vertical line from there straight up to the top here. And my job right now is to sort of, I'm trying to think about how this vertical plane is slicing the cylinder. So I'm going to draw another parabola, but it's, that's not good. I think it's gonna go like, yeah, I'll get it. Something like this. Eventually come down here like that. That's what I'm trying to do. And that's supposed to look like a parabola also. But that's, so let me show you what I don't want graphed anymore. I don't need any of these lines. Okay, and now we can sort of shade some of this stuff. So the top, I'll go ahead and do first here. Okay. So that's the cylinder. That's on top. Z equals 1 minus x squared. On the bottom, I'll go ahead and get a shadow of the solid down in the xy plane. So this is my region R that we'll be integrating over. Okay. And we call that R. This curve right here is also a plane. Well, I'll put it on the side here. So I'll shade it first, I think. So maybe in blue, I'll do this. And again, now what I've got here is a plane in front. Okay. There's a back. I don't know how much you want to deal with in this picture. It gets pretty complicated. So on this side here is y equals, what is it? That's x equals 1 minus y. Or you could look at that as y equals 1 minus x either way. Okay, that's our solid. Okay, so I need to change the orders of integration around a little bit here. I'm going to try and get all this in. Okay, so let's see if we can pull this off. That was not supposed to happen. Okay. So I'm supposed to rewrite this as triple integral And this is supposed to be dy dx dz. Got it. So the function is still f of x, y, z, but then we'll do dy dx dz. Okay. So y goes left and right. So the limits on y need to be a left surface and a right surface. Okay. So we're going to figure that out. On the left, I don't know. I'm going to shade it in red, and you guys help me figure out what this is. On the left, in red, what is this? This is the part where you guys have to help me out. What's that red thing on the left? It has to be y equals something because this is a limit for y. Anybody? Y equals what on the left? Correct. Y equals 0 on the left. That's your lower limit on y. 0. To what? Well, on the right, you got to do the right surface. So if x is 1 minus y, I think that means y is 1 minus x, right? So that's your right surface, left to right. It's still surface to surface, but on the right it's 1 minus x. Any questions? Now, what's left are x and z, okay? So we need to project this region into the xz plane. Okay, so right here, you can kind of see it, but I'm gonna need to draw it, I guess. So let's do the projection into the xz plane. Okay, so I just basically need to copy that red region that I drew. So let me just do that down here. I think I'll do it by shading it red again, but let me get that paraboloid going. Now I've got my x-axis going to the left. I hope you don't mind. So that's my region R. Notice x is 1 right there. And then on the other end, x is 0. But remember, I'm going curve to curve here. And these are limits for x that we're working on. X goes left and right. So the curve on the left has to be x equals something, and the curve on the right has to be x equals something. So question is, what is x on the left? I'll tell you the curve. That curve right there is z equals 1 minus x squared, where x is positive. So anybody want to tell me? I guess you x is going to be plus or minus, but let's go with the positive square root of what? It looks like 1 minus z to me. Do you guys agree with that? Yeah, root 1, 1 minus z. Thanks, Alicia. So remember, x, I probably shouldn't have drawn it this way. my x-axis is going to the left. That's not a good thing. But yeah, I feel like I've weakened my argument by doing that. I hope you can see x is smaller on the right and bigger on the left because I've got x going to the left as it grows. So what's, I guess I should just say, hey guys, what's my lower limit on x? Correct, lower limit, I think that's Alicia that's saying 0. So we're in lower limit on x is 0. And my upper limit on x is where x has gone positive. X is the square root of 1 minus z. So that I'll put down as my upper limit, 1 minus z. Okay, so that's a, why did I draw it like this? You guys are gonna have to forgive me for a second. I hate myself, but I'm gonna change this. Okay, so a better picture. Don't know why I thought it was okay to do that. So anyway, x goes to the right now and z, and then the parabola coming down was z equals 1 minus x squared. So x is the square root of 1 minus z. And on the left, x is 0. And remember, it's left curve to right curve. That's why I'm frustrated about the way I did this. So we always do left to right on x, lower to upper, and this is region R here. Okay, so you're going to have a curve to curve. On the left, x is 0. On the right, x is the square root of 1 minus z. And then we have to project onto the z-axis. So let's do projection onto the z-axis. Okay, and for the z-axis, this region just goes from here to here. Oops. Okay, so down at the bottom, z is clearly 0. And at the top, I think z is 1. So we'll have z go from 0 to 1. And that problem is done, but it's a tough, tough problem. So I want to give you guys a chance to ask questions. There, to let you know, with 3 variables, there are 6 ways to arrange them in terms of orders. The normal order for triple integrals is dz, dy, dx, but there are 6 orders altogether. Three things can be ordered in 6 ways. So you can do dz, dy, dx, dz, dx, dy, dy, dx, dz, dy, dz, dx, and so on. There are many ways to integrate with triple integrals, and there are problems in the homework that do just this. They start with a problem and they say change the order of integration like this. And the reasoning is, first of all, some orders are easier than others, but I think second of all, if you can pull this off, you can do just about anything. Okay. This kind of problem is very annoying to do. It's tedious, and I think you learn better on a problem like this than you learn just about anything. So when you see problems like this, please do them. Okay. We need a break, so I'll see you guys at 7:40. Okay, so these are all the formulas that we need for the first moments. to each of the coordinate axes, sorry, to the coordinate planes. So the only thing that's left is the 0th moment. To remind you, 0th moment is mass. Okay, so 0th moment, that's just mass. And we use just an m for that, okay? So m is the same integral, but there's no distance involved. So integrate over q, and then just do delta of x by z dv. Someone was asking about videos. I think everything's posted video-wise with correct. Videos are posted with corrections. Obviously, I'll have more to post tomorrow. But feel free to jump in there and watch those videos. Okay, so the 0th moment is mass. And so then we do center of mass. So x bar, y bar, z bar is the coordinate of the center of mass, which is super important in physics. We talk about how the planets in the solar system, we say they rotate around the sun, but they really rotate around the mass of the center of mass of the solar system. All the planets rotating around the solar system's center of mass, including the sun. Of course, the sun is so massive, it sort of almost defines the center of mass, but I imagine there's a little wobble around that. Center of mass, x bar, y bar, z bar, and as you know, center of mass, you always take the moment and you divide by the total mass. So x bar would be the moment that involves x distances. The moment that involves x distances is the moment to the yz plane. So you have to remember x bar is sort of an average. So you're averaging the x distances, which are m, y, z over m, which is so frustrating. But you just have to remember whatever variable is not mentioned is the coordinate, the center of mass is coordinate that you're doing. So in x bar, you just don't want to use the, there shouldn't be an x mentioned in the moment. And of course, y bar, you don't mention the y, so it's an mxz over m. And z bar is mxy over m. Okay, so that's all just really bad because it's a lot of integrals. Okay, so any questions about any of this? I know we have to do examples, so I'll do that shortly. But don't forget, there are second moments also. So that's coming next. So second moments, those are moments of inertia. Okay, and don't forget that mass, the 0th moment, mass is also just inertia. Okay, so inertia is resistance to force. So the 0th moment is resistance, is mass, which is resistance to a kind of a force that pushes in a linear fashion. The second moment, the moment of inertia, is also resistance, but it's resistance not to a force, but to a torque as you try to make a rotation around an axis. If an object is resisting that force to rotate, then that's the moment of inertia that's causing that. Okay, so the second moments, remember, are always mass times distance squared. Okay. And the distance, and we rotate about an axis. So you're not going to rotate around a plane. That makes no sense at all. So when we talk about rotation about an axis, if you're rotating around the x-axis, the distance from the point to the x-axis is the square root of y squared plus z squared, and you're going to square that so that the square root goes away because it's distance squared. So you're going to have a moment of inertia about the x-axis, and it's the same thing. You're integrating over the solid, but the distance from the point to the x-axis is the square root of y squared plus z squared, and you're squaring that. So you're just going to have y squared plus z squared, okay? And then times mass density times volume. So that's distance squared times mass here. Okay, and that's moment of inertia when you cause rotation about the x-axis. So maybe I'll put that in parentheses. This one's about the x-axis. And then the others are just like that. The moment about the x-axis doesn't mention x in the distance. It just has y squared and z squared. Okay, and the pattern continues with the other moments. Okay, so I'm just going to doctor that up a little bit and customize it to each axis. So there will be an IY and an IZ. So IY will have two different numbers in here. Okay, moment about the y-axis is IY, and that has an x squared plus z squared for the distance squared. And the moment about the z-axis, distance squared to the z-axis is x squared plus y squared. Okay, so those are the second moments. And again, that's rotational inertia, super important when you design motors or other things that rotate. And the moment of inertia also, it goes straight toward kinetic energy. So remember, kinetic energy when you move along a linear path is 1/2 mv squared, m being the inertia. Kinetic energy when you spin something like in a motor, that's 1/2 I omega squared. I is the moment of inertia. Omega is the angular velocity. Okay, so let's do a quick example here. Try and get one in before you guys have to go. Oops, this last one should be IZ. I think we're okay otherwise. Any questions out there? When are the lecture notes going to be on Canvas? Are they not? I know the videos are posted, so Chris, I'll get those posted. If they're not, I thought they were. Let me see. I'm trying to find one that won't take an hour. I got 2 pages left of notes, so let's see what we can do here. I'll bring up these formulas again as we need them. Okay, so we're going to find the z-coordinate of the center of mass. Hang on. For the solid, this looks familiar. It's a little different from what we just did. For the solid, this one is bounded by the planes. And these are kind of simple. The first one, x plus z is 1, is the hardest one, but notice there's no y. Oops, x plus z equals 1. X equals 0 and z equals 0. Okay, so that's 3 planes and the parabolic cylinder. Z equals 1 minus y squared. And of course, we need a mass density function. So this is a constant, thank goodness. So with mass density, delta of x, y, z equals, I think it just says 4. I want to slide back and remind you guys of something because I forgot to say it. I meant to say it, but I'm going to go back. Just to remind you that for delta, the mass density function, I just want to remind you the book uses rho for density. Okay. But we use rho as one of the coordinates in spherical coordinates. And you'll be doing centers of mass in spherical coordinates. So if you use rho, you're going to have 2 different rows that are completely different things. I just use delta, it kind of solves the problem. Okay. I don't know why they don't worry about that, but they don't. Anyway, so here's our solid. We've got to draw this thing before we can hope to get anywhere with it. Okay. Let's go ahead. Here's my z-axis. I'm going to have a y-axis like this, I think. Because I have a parabola z equals 1 minus y squared, so I'm thinking of that right now as I proceed. Something like that. I'm gonna try a better job. Oh, that's beautiful. Okay. And then my x-axis is going to come straight out here. Like that. Now this is a parabolic cylinder, so I've got to kind of, let's see if I can do some guidelines real quick here. Oops. Working on it. Hang on. Okay, so that's a guideline. This is a guideline. I'm going to have a vanishing point guideline up here just to kind of make sure I'm making this vanish in the right place. Copying this thing. Just to help you see this, I'm going to probably have to erase this, as you'll see as we go. Okay, so that's my parabolic cylinder there. I'm going to get rid of some of these guidelines. A lot of this is going to get erased, just FYI. Don't get too attached to it. So let me see, boom. Oops, I didn't want to erase that. Okay, so that's my parabolic cylinder. But then I also have this plane, x plus z equals 1. I'm going to draw that here. So maybe we draw that in the xz plane. So that's just a diagonal line that kind of cuts down like this. This is x plus z equals 1. Okay, z equals 1 minus x if you like. So I'm going to draw that coming down like this. Okay. And then more guidelines. Okay, watch what I do. I'm about to cut the parabolic cylinder with the plane here. It'll take me a couple of tries. That. And on the other side also, this one's harder. Not bad. Okay, now I'm going to raise a bunch of my crop. So pardon me while I do that. I don't like the way those green ones don't grab to the top. I don't know if I can fix that. I'm going to try and fix this a little bit. We'll see how it goes. Just moving that up a little. That's pretty good. Okay, so and maybe a little coloring just to wrap it up here real quick. Okay, so that's the green is x plus z equals 1. And I'll do the cylinder real quick. Try that again. Okay. I think this is pretty good. I'm content with that. I hope you guys can see that. Attachment issues. Alicia, that's hilarious. I hope you mean to be funny there, because it sounds funny. I don't know. Anyway, what's left here is to decide how to integrate this thing. Let me just show you kind of the idea here. We're gonna toss this around a bit. Okay, so right now I'm gonna have some function inside here, and the question is, do I do dz, dy, dx like I normally like to integrate? This would be okay if I had a a bottom surface for the lower limit, which I do. The bottom surface on z would just be 0, okay? But then the top is no good, because the top is the green and the red surfaces. Okay, I can't do 2 surfaces as a top unless I want to split this into 2 different integrals, and it looks really bad to go from bottom to top. Can you guys see the top is made of the green and the red, and that I can't have 2 top surfaces? The upper limit needs to be just 1 surface. Okay, so bottom to top doesn't work as surface to surface, so I'm going to change this. Okay, we're not going bottom to top. Just get rid of it. What about left, right? That would work. I don't like it. Left would be the pink surface on the left, and right would be the pink surface or the red surface on the right. That's pretty good. What if we went back to front? So what if we had a back surface and a front surface? Okay. Back meaning, what is the value of x in the back? X equals what? X equals 0, correct. So your back surface is where x is 0. So let's do a lower limit as the back. And then what is x in the front? That's the green surface. And I'm actually going to do that in green just to make it clear. So x is 1 minus z, yeah? Okay, you guys okay with that? 1 minus c, good, 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 good. So, but 1 minus c is a bigger value of x than x equals 0. So the back is the lower limit and the front is the upper limit. It should always go to back, from back to front on x. Okay. Oh, sorry, 1 minus z, my mistake. Okay, any questions? Okay, so I think those are limits on x. I need to change these variables of integration here. So right now I gave limits for x. So x is done. What I need to do is figure out the projection into the YZ plane. And if you look at that, that's just that inverted parabola. Okay, so let me do that real quick here. YZ plane, got it. It's just that parabola here. And remember, the parabola is z equals 1 minus y squared. And on the bottom, you also have a boundary where z is 0. So see, if we're going to go curve to curve, it should be bottom to top. So the next is going to be z. Okay, and then we'll do y last. Okay, so this is a bottom curve. Oops. Where z is 0. To a top curve where z is 1 minus y squared. Oh, I did not mean to do that. I gotta move some things. It's all too crowded, so I'm just rearranging. Okay, so the top curve, again, it's curve to curve, 0 to 1 minus y squared. So that's a top curve. Okay, and then we project onto the only axis that's left. Let me clean this up a little bit. And let me do this in another color here. Okay, so limits on, so again, the horizontal axis here is y. I'm looking at the projection again, you guys. So y is the axis we're projecting onto, and y is going to go from -1 to +1. Okay. So once you've projected into the xy plane and you're integrating over something like a region R here, you go curve to curve when you're in the plane, and then that two-dimensional region projects onto the z-axis. So the green line here, I'll do it in green, hang on. The green line is the projection of R onto the y-axis. Okay, so again, that makes y go from -1 to 1. So that's again point to point. Okay, so surface to surface, curve to curve, point to point. That's the general form for setting these up. Okay, so any questions? It's 25 after. Oh my goodness. All right, this thing's asking for the center of mass, a z coordinate of the center of mass. So just as a reminder, z coordinate of the center of mass is z bar. So z bar is what we're looking for. And as also another reminder, this is mxy over m. And the reason why it has mxy is because mxy is the thing with the z distances in it. So mxy is a triple integral with a z, then density at xyz times dv. And you integrate over the solid q. Okay. And of course, we'll do the mass later. And there's only 10 minutes left, so we're not going to get much more than just writing down what these come out as. But again, the real battle here, everybody, especially on these harder problems, is just to get the thing set up. That'll be worth most of your credit on these problems. I'll just go ahead and copy these limits over. 0 to 1 minus z. Then 0 to 1 minus y squared. And then, of course, -1 to 1. Now, the moment to the xy plane, you just multiply the distance to the xy plane from a point, which is z. And then density, remember, was just 4 times dv, which will be, let's see, what's the order? dx, dz, dy. Is that what they asked? Please tell me it is. Oh, it doesn't ask. Good. dx, dz, dy. Okay. That looks like a pretty easy integral, but to let you guys know, it took me about 3/4 of a page to do that. And I write pretty big, I guess, so, and there's large margins. So regardless, it took me a page almost. And I'll just let you know, because we're almost out of time, that thing comes out, that ends up being 152 over 105. Okay, make sure you can evaluate these. The mass is just a triple integral of the density function. Okay, and over q. All right, and so this is going to be the same limits. but all you have is density, which was 4. Okay. And already worked that one out. And just to save time, this one comes out to be, hang on, it comes out to be 16/5. Okay. And so then the z coordinate of the center of mass is z bar. And so this is the mxy/m. And so easy enough, 152/105 divided by 16/5. And somehow when you do that, it comes out as 19/42, just simplifying and reducing these fractions, which is approximately 0.45. Okay, so that's just about halfway up, which sort of makes sense. The other coordinates of the center of mass will be equally complicated. I'll try and get some problems in next time that involve more computations than what I was able to do here. It's 8:30 now. I should say that you can note that you can use symmetry for center of mass. Only if one, the object is symmetric about one of the coordinate planes. Well, let's just say the object is symmetric. Let's say with respect to some variable. But also the mass density has to be symmetric as well. I'll say in the same way. So it doesn't make sense to say the center of mass is in the center of an object if one side weighs more than the other. Even if the object is symmetric visually, if the mass is not distributed symmetrically, then the center of mass will not be in the center. But our object has left-right symmetry. And uniform mass density. Which tells us both of those facts are required. You guys, which y coordinate for the sorry, which coordinate of the center of mass would be 0 given the symmetry of the shape and the uniformity of the mass density? Is it x bar, y bar, or z bar? Y nar, I like it. So that's like gnarly y. So the left and the right on y are symmetric, and because of because the mass is the same on the left and the right, the y bar coordinate has to be 0. But x bar doesn't, because there's not a back front symmetry, only left and right. Okay, So we'll just say this tells us that y bar is 0. Okay, and that's it. That's all we got time for. So I'll try and get some stuff posted, you guys. And this lecture is not done, so I'm not going to post this video till after Wednesday. All right, so take care of yourselves. I'll see you soon. Okay, so let's do another problem where we want to find the moment of inertia. About the z-axis. For the solid bounded between the xy plane and z, well, I should say in the paraboloid. Let's do z equals 9 minus x squared minus y squared. And then let's have a mass density proportional to the distance to the origin. So with mass density proportional to the distance from a point, any point, x, y, z, to the z-axis. Okay? All right, so that's a lot. So let's go ahead and just remind ourselves. So we have a formula, and I guess I can do a quick little sketch of this thing. So here's a paraboloid like that. Let me get that. Paraboloid with cross section. It's a circle. Tilted sideways, looks like an ellipse or some strange polygon. Okay, keep trying is what they say. Here's a good one. Okay, so the solid is called Q, because that's what I just called it. And let's see here. We could do mass density. So delta of x, y, z is the distance from x, y, z to the z-axis. So that is by definition r, and it says it's proportional. So this is k times the square root of x squared plus y squared, which is the distance to the z-axis. Okay. So that's the mass density function. Okay. And I think we're pretty good here. Maybe on the top, we'll just kind of put in our surface. So on top you have z equals 9 minus x squared minus y squared. On the bottom here, z is 0. And maybe we've got a region down in the bottom here we'll call R. So give me a second, we'll do a little bit of a number on this. Okay, so down on the plane, that's R. Okay, and just the moment of inertia, the formula for the moment of inertia for solids, well, about the z-axis, you do a triple integral over the solid, and it's always equal to the distance to the z-axis squared. And once again, the distance is the square root of x squared plus y squared, but you're squaring that. So you do x squared plus y squared, that's distance squared, times mass, which is mass density, dB. Okay, so that's just the formula for the moment of inertia about the z-axis. Any questions? And again, just to remind you, inertia is mass, which is resistance to force in a linear path. Moment of inertia is also inertia, but it's resistance to torque. Which is a rotational force. Okay, so let's go ahead and start figuring out what this thing has to look like. So we have this triple integral, and we can put in our x squared plus y squared here. And then the delta is going to be k times the square root of x squared plus y squared. And then I'm going to put a dz here, and then dA. I'll do dA now so that I don't have to decide what I'm going to do with in the xy plane when I get to it. I'll probably switch to polar because I'm integrating over a circle. But remember, the innermost limits have to be surface to surface. So we're doing a limit for z, so z goes bottom to top. The bottom surface is z equals 0, right? And the top surface is 9 minus, z equals 9 minus x squared minus y squared. So those are limits on z. And then there will be limits on x and y in the xy plane. But we'll just say, okay, in the xy plane, we're integrating over the region R, that circle that I drew in the diagram. Okay, is there any question about the setup? It's not done being set up, but is there any question about the setup yet? And let me look at my chat real quick because it's lost. I don't see any messages there. Feel free to unmute yourself and let me know if you have a question. So that's just a formula for the moment of inertia, and of course I'm trying to apply it. We could evaluate what we've got here. Wouldn't be a big deal. So let's take another step here and say, all right, well, this is, I'm going to keep the double integral over region R. And what you have here is just a function of x and y. Well, let me do one more step. So we're going to integrate on z. We're going to go from 0 to 9 minus x squared minus y squared. Okay, but then maybe we'll bring the k out front. Okay, and then what you have is a x squared plus y squared to the 1.5, which is 3/2. So let's just change this to x squared plus y squared to the 3/2. And that'll be dz and then dA. Okay. And then that's a constant as far as z is concerned. So we can just do one more step, write a double integral over r. Now I'm going to go ahead and take an antiderivative with respect to z. So you're just going to have an x squared plus a y squared to the 3/2, like that. And then times z. But z is going to go from 0 to 9 minus x squared minus y squared, like that. And then it'll be dA. Now, Bilal. Oh, okay. So now, are you talking about Bilal? Are you talking about for the IZ formula? Yeah, for IZ. Okay, so I would just want to refer you back to the notes from last time. We're just extending our discussion. Here are the formulas for the second moments or the moments of inertia. So you'll have that in your notes. And moments of inertia, you just do distance squared. So the distance to the z-axis from a point is the square root of x squared plus y squared. And moments of inertia, you have to square that, so it gets rid of the square root. You just get x squared plus y squared. That's the distance squared. Okay, so here we are. And so let me just take one more step before we go to polar. So we'll leave the k out. We've got a double integral over r. We've got x squared plus y squared to the 3/2. Then you've got z, which is going to just be 9 minus, I'm going to put this in parentheses, so it'll be x squared plus y squared in parentheses, because that's going to be r squared in a second. Okay. And then it'll just be dA. Okay, and then for, we're going to switch to polar. Okay, so in polar, you know, x is our cos theta, y is our sine theta, and that doesn't actually come up because all you have to deal with is x squared plus y squared, and that's r squared. But don't forget the real trick is that dA is r dr d theta. Oops. Okay, any questions? And then we'll have to put limits on this, but that shouldn't be too hard. It's just a circle, I think of radius 3 that we're integrating over. Okay. So here we go. This will be k double integral x squared plus y squared. That's going to be r squared to the 3/2. And then you have 9 minus r squared. And then dA is r dr d theta. Just reminding you that d theta is not a length. It's r d theta that's a length. And so dr times r d theta is an area. Okay, now we have to, again, we'll integrate, I think we're integrating over this circle of radius 3. Let me just kind of clarify. Yeah, I put that down pretty well there. So let's get that going here. Okay. And don't forget, we sort of take these slices from the origin out, like this, when we go into polar, and we think of these sort of radial slices, taking little pieces of the slice, like that. at the beginning of the slice, R is 0, so that's a lower limit on R, and on the outer edge of the slice, R is 3. Okay. And don't forget, we're going to have theta going from, well, we have to cover the circle. So our theta is this guy. Okay, so limits on R are 0 to 3, and what are the limits on theta? Anybody? Well, you got to cover that whole circle. So when R goes from 0 to 3, you'll fill up this little slice here. But then theta has to vary from 0 to 2 pi to fill up the circle. Okay? So I'll put 0 to 2 pi on the for the limits for the integral on theta. Is there any question about any of that? Thanks, Chris. Okay, now this is just plug and chug. In fact, these are constant limits. So you could break this into 2 integrals if you want. You could do k times an integral from 0 to 2 pi, just d theta. All the rest of it is just constant. So you could multiply by the other integral from 0 to 3. And that's an r to the third, and there's another r. So I think you end up with a 9r to the 4th minus r to the 6th. And that'll be dr, I think. Just gonna make sure I'm not losing my mind. That's an r to the 4th. 9r to the 4th minus r to the 6th. Yeah. Okay. So should be done in just 1 second. K times 2 pi times, let's see, 9/5. Yuck. R to the 5th from 0 to 3 minus 1/7. R to the 7th from 0 to 3. That's horrible. Okay, so 2k pi. And so 9 is a 3 to the 2nd. So you could almost see this as a 3 to the 2nd times a 3 to the 5th over 5 minus a 3 to the 7th over 7. You know what I'm saying? See where I'm getting at? So you could just look at this as 2k pi times 3 to the 7th times a 5th minus a 7th. What about that? And so I don't know what a 5th minus a 7th is. So it would be 7 minus 5 is 2 over 35? I don't know. But 7 minus 5, that's 2. So I think it would be 4, I don't know, 4k pi. I'm just going to leave a 3 to the 7th in there because that looks much better than 3 to the 7th looks. I don't want to know what 3 to the 7th is. And I think it's over 35. Okay, and I'm thinking that's just gorgeous. It's beautiful. It makes me smile. All right. That's all we're going to do for that section.